Hey everyone, welcome to the video on how to approach spectroscopy questions. In this video, we'll go through a sample exam question on the more difficult side that consists of analyzing the mass spectrum, infrared spectrum, and both MMR spectrums of a sample organic compound. This type of question is very common amongst exams, and it is important for you to be familiar on how to approach and tackle these questions in a systematic manner, as they often make up a huge component of the exam. When you're given 4 different spectra of an organic compound, it's important to start with the infrared spectrum, followed by the carbon-13 MMR spectrum, the mass spectrum, and analyze the proton MMR spectrum last, if necessary. We start with the infrared spectrum because the infrared spectrum will provide us information on the type of covalent bonds, as well as the functional groups present in the organic compound. Looking at this infrared spectrum, we can clearly see that there is a carbon to oxygen double bond, a carbonyl group present in the 1680 to 1750 wave number range. You can find this on the NASA datasheet. There are a couple of signals on the far right hand side of the infrared spectrum. However, these could be due to other bonds found in the compound, but could also due to contamination of the sample when analyzing its infrared spectrum. So usually I recommend not paying too much attention on the far right hand side of the spectrum, as you often get a crowded set of signals that are difficult to analyze. Once you've looked at the infrared spectrum and have identified the unique functional groups or the bonds, we need to start thinking about what type of compound could exhibit these signals. So in this infrared spectrum, we've found that there is a carbonyl absorption. So we need to start brainstorming about what function could this be. What comes to mind to start with would be an aldehyde, a ketone. Both of these are carbonyl functional groups, and they both contain this special bond. Other functional groups that contain this bond include carboxylic acids and amides. However, those two functional groups are not consistent with this infrared spectrum because a carboxylic acid would also have an oxygen-hydrogen absorption on the far left-hand side of the spectrum, which we do not see in the spectrum. An amide will also provide an absorption signal in the wave number range above 3000. Again, we don't see that in the spectrum. The other function that could be plausible is an ester. An ester also has a carbonyl bond as well as a carbon to oxygen bond, which is around in the right-hand side region of the spectrum. Once you've brainstormed the plausible functional groups that's consistent with the findings in the infrared spectrum, it's time to move on to the carbon-13 MMR spectrum. There are 2 main things you want to obtain from the carbon-13 MMR spectrum. The very first one is presence of any chemical shift signals on the far left-hand side of the spectrum. So this includes anything above 160 ppm. And here we can see that clearly there is an absorption at around 170 ppm. If you look onto the data sheets, you will see that this corresponds with either a carboxylic acid absorption or an ester carbon absorption. If we correlate this finding to what we said in the infrared spectrum, we can cross out the possibility of it being a carboxylic acid. As I said earlier, carboxylic acid will also give you an oxygen-hydrogen absorption on the far left-hand side of the infrared spectrum. So by combining your findings in infrared spectrum and the far left-hand side of the carbon-13 MMR spectrum, we already identified that the functional group is definitely an ester. It cannot be an aldehyde ketone, as the carbon environment in these 2 functional groups will give you a chemical shift that's above 180 ppm, so a bit further to the left in the spectrum. The next piece of information you can obtain from looking at the carbon-13 MMR spectrum is the number of signals. The number of signals, which there are 4, suggest the number of chemical environments for the carbon atoms in this molecule. So we know that there are 4 chemical environments for the carbon. And this tells us the minimum number of carbon atoms in the molecule. So we know that this molecule must have at least 4 carbon atoms. This is because it's not physically possible to have 3 carbon atoms when there are 4 chemical environments. At this point, what you want to do is draw a sample ester molecule that has 4 carbon atoms. And the one that first comes to mind for me is ethyl ethanoids, which has the molecular formula of C4H8O2. What you want to do next is calculate its molecular mass and correlate this data with what you see in the mass spectrum. So the molecular mass of this ester would be equal to 4 carbons plus 8 hydrogens and 2 oxygen atoms. And this gives us a number of roughly 88 grams per mole. You want to see whether this molecular mass has the same number as the molecular ion peak of the mass spectrum. And fortunately for us, in this case, the molecular ion peak is also at a mass to charge ratio of 88, which is consistent with the molecular mass of this ester of 88 grams per mole. Does that mean we have found the answer? Unfortunately not, because this is not the only ester molecule with this molecular formula. There are a couple of other ester molecules with 4 carbons as well. At the moment, we've exhausted all the information provided by the 3 spectra we've analysed so far. When you get to this point, if you still haven't found the structure of the compound, then you can move on to the last spectrum, that is the proton NMR spectrum. I want to reiterate, you should only analyze the proton NMR spectrum last and only do so when necessary. Before you take a closer look at the proton NMR spectrum, it's important to draw the structure formula for all the isomers with the same formula as ethyl ethanoate that we drew before. The first piece of information you should look at and obtain from the proton NMR spectrum is the number of signals it presents. There are a total of 3 signals, which suggests that there should be 3 proton chemical environments in the molecule. If you take a quick look at the 3 molecules I've drawn, you can see that the middle molecule, which is propyl methanoate, has actually got 4 proton environments. There's one here, the second one over here, the third one over here, and the fourth one over here. If this is the molecule that we're analyzing, this will instead give us 4 signals in the proton NMR spectrum. So because we've only got 3 signals, we know that this ester is not the correct molecule. Once you've looked at the number of signals in the proton NMR spectrum, it's time to look at the relative intensity under each signal. The numbers underneath each signal represents a relative number of protons in each chemical environment. If we take a look at the first ester molecule, there are 3 proton environments in the first carbon on the right hand side, 2 protons in the second chemical environment, and again 3 protons in the last and the third chemical environment. The numbers 3, 2, 3 corresponds with the numbers and the relative intensity under each signal. If we apply the same idea to the second ester molecule, we again have 3 protons, 2 protons, and 3 protons. So these are all consistent. So unfortunately for this question, we cannot use the relative intensity to distinguish between these 2 isomers. What we can do next is look at the splitting pattern. We can see that in the proton environment that has 2 protons, this gives us a quartet. And if we recall to the rule, the number of peaks in a signal is equal to the number of adjacent protons plus 1. We know that if this is a 4 split pattern, the number of adjacent protons next to this chemical environment will be 3. For both of these molecules, this corresponds to this particular chemical environment that I'm circling in blue. In this chemical environment, these 2 protons are adjacent to 3 other protons in a different chemical environment, and these 2 protons are again adjacent to 3 other protons in a different chemical environment. So both these 2 proton environments will produce a quartet signal, one with 4 splits. However, now it's important to see that these 2 proton environments are actually different between themselves. This proton environment is connected to a carbon atom that has a single bond to an ester oxygen, whereas these 2 protons are bound to a carbon atom that's next to the carbonyl carbon. Let's call this proton environment 1 and this proton environment number 2. If we go to a chemical shift data on the right hand side, we should go through the list and identify these 2 proton environments. The first proton environment is over here, where the 2 protons are bound to a carbon atom that's next to an oxygen via a single bond. The second proton environment is this one, where the proton is next to a carbon atom that's adjacent to the carbonyl carbon, which is the carbon atom with a double bond with the oxygen atom. And if we go back to the spectrum, we can see that the quartet signal is around 4 ppm. This is consistent with the first chemical environment, which means the protons that produce the quartet signal must be in this exact proton environment. This is consistent with what we said in the first molecule at the top, and not consistent with the bottom molecule. As in the bottom molecule, the 2 protons would instead give a quartet signal between 2.1 and 2.6. So our final answer is ethyl ethanoate. This concludes the video on how to approach spectroscopy questions.